morning, everyone, and thank you very much for sticking around till the last day of this workshop. Makes me happy that you are here to listen to my talk. And I would like to thank the organizers of the IWE EEM 2020 for inviting me here and giving me the opportunity to present my research to you all. So today I'll be talking mainly about spray combustion instability. And if time permits, I would like to slightly touch upon this topic of direct combustion noise from turbulent spray flames. So I'll give you a brief background on our research. So as you might be aware that gas turbine engines are used for applications of propulsion and power generation. And in the combustors of these gas turbine engines, you can inject fuel as in a gaseous form, which could be leading to premixed or non-premixed combustion, or you can directly inject the liquid fuel as a spray. But when you are having turbulent combustion inside the combustor, it is often accompanied by what we call combustion noise, which is a byproduct. And this is basically coming from the heat release rate fluctuations occurring inside your combustor. So the motivation for our study is as follows. So in this figure, you can see the noise emission standards that are set by the International Civil Aviation Organization. And over the years, you can see that the norms are getting more and more stringent. So the allowable noise levels, which is expressed here in terms of EPNdB, which stands for effective perceived noise level in decibels, goes down and even more every year by year. And over the last few decades, it has become more and more stringent. And another issue is that, so to keep in line with these norms, researchers have invested a lot of research to reduce the other noise sources from engines. Like, for example, you have the jet noise, and then you have the turbo machinery noise, like the fan noise. So a lot of research has been done to drastically reduce these noise levels. And this is showing you a typical noise contribution from different sources in a typical gas turbine engine. And you can see that you have the jet noise and the fan noise and also the combustor noise. Now, since these noise sources have been suppressed to a good extent, the combustor noise or the combustion noise has emerged as one of the dominant sources. Now, this is the problem is further aggravated by the introduction of what we call the lean burn combustors, because we want to reduce the NOx and other emissions. So we introduced these lean combustors, but the problem with lean combustors is lean combustion is inherently more unsteady, and it leads to more noise. And it's not just the noise. The problem arises when you have a coupling between the acoustics of the combustor and the heat release rate fluctuations. So here I've shown a schematic which shows the two pathways by which the coupling can occur. And once this, if there is a suitable phase relation between the heat release rate fluctuations and the pressure perturbations, the self-excited oscillations will grow and lead to what we call thermoacoustic instability or combustion instability. And this is dangerous. Like once this starts occurring, there's like loud noise at discrete tones, and the vibrations caused by this can actually damage your combustor components. So this is why we need to investigate the mechanisms behind this. But today, what I'll be showing you is our attempt at understanding how the fuel flow rate fluctuations influence the combustion instabilities in a backward-facing step combustor configuration. So the schematic of our setup is shown here. We have the fuel spray, which is coming out, and this is injected through many ports. Like in this study, we have used like 7 ports through which fuel is injected. And the flow rate fluctuations are taken into consideration using a model, which I'll introduce soon. And then you have the air coming in like this, so it's a typical cross-flow configuration. And then you have the flame that is formed behind the step. And we want to see how the fluctuations in the flow rate will affect the combustion instability in this case. So this is the computational domain and conditions for this study. You can see this is the entire domain. So you have a plenum section followed by an inlet duct, so the air flows in through a opening over here into the plenum and then goes through this inlet duct and is introduced inside this combustor. So the combustor is zoomed in over here. So you have the fuel coming in vertically, is injected vertically upwards, and the cross-flow air coming in. And the fuel conditions here, like we maintain a global equivalence ratio of 1, and the fuel used is kerosene. And we assume that when the fuel is injected from these ports, a spray is already established. So the droplet size distribution is given by this Nukiyama-Tanasawa PDF, which is fitted to a previous experiment on a real gas turbine combustor performed by Moriai et al. So these are the typical LES governing equations that you might be familiar with. So we are solving the filtered equations of continuity, momentum, energy, and species mass fractions. To take into account the subgrid turbulence, we use this dynamic Smagorinsky model. And for the turbulent combustion model, we use this dynamically thickened flame approach. And then you can see that there are some source terms in each of these equations. These source terms are to take into account the phase coupling between the dispersed phase and the gas phase. And then for the reaction of the kerosene fuel that we are using, we use a two-step reduced chemistry to keep computational costs realizable. And then these are the governing equations for the dispersed phase. So the gas phase is treated as an Eulerian continuum, while the droplets are solved in a Lagrangian framework, and the position, velocity, temperature, and mass of each individual droplet is tracked. And the evaporation of these droplets is considered using a non-equilibrium Langmuir-Knudsen model. So this is the model that we use for the flow rate fluctuations. We call it the variable mass flow rate model. It is a simple model that has been derived from Bernoulli's principle. So what we have here is the fuel injection velocity is a function shown like this, where this P naught is the injection pressure. So the P naught is the summation of the average pressure. So initially, all these simulations have been performed for an average pressure of 1 atmosphere. So that's the average pressure plus the pumping pressure, which is given by this equation. So you can see that, and then there's another term called this is the instantaneous pressure. So this P now minus some phase difference term. This is the pressure at the time instance T now. And we are applying a phase shift to this this model. So this phase shift, what it basically means is you are creating a lag between, you're creating a phase difference between the fuel injection variation and the pressure oscillations that are occurring inside the combustor. So ideally, when we are having this kind of model, so if this pressure P naught, injection pressure, is larger than the pressure, this P that is shown here by the point. So this is the pressure measured just outside the fuel injection port. So if the injection pressure is larger than this, of course, we will have some fuel injection which will be given by this velocity. But when you have the pressure, this outside pressure, if it becomes larger than the injection pressure, ideally the fuel should be cut off. So think of it as a non-return valve. But in this case, we still inject a small quantity of fuel using this velocity V min. And the purpose for doing this is over one cycle of pressure oscillation, we wanted to maintain the global equivalence ratio to 1. So that was the only reason why we used this very small injection rate to keep the equivalence ratio at 1. So we investigated 5 cases. So first case, these are like named as cases NA1 to NA5. The first case, we don't apply the model. So it's just like constant fuel injection rate, and it's like the case where you have some combustion instability occurring without this model. And then we start applying the model from case NA2 to NA5. And the difference is we start increasing this phase shift. So in case NA2, we apply the model, but we keep the phase shift between the fuel flow rate variations and the pressure oscillations 0. And then we start increasing it slowly to 90, 180, and 270 degrees. So first I'll show you the results for the case NA1 where the model is not applied. So you just have a constant fuel flow rate coming in from all these ports. And you can see like a periodic large vortex is generated behind this step, and the flame is stabilized in this recirculation zone. You can also see the droplets, which are represented by these blue entities, flowing downstream, dispersing, and the droplet count is reducing as you go downstream because of evaporation and combustion. And this red isosurface that you see is the gas phase temperature at 1500 Kelvin. So then we confirm like what kind of fluctuations are happening. So we look at the pressure fluctuation, which is the pink curve, and then this is the heat release rate, the blue curve. So this is the total heat release rate fluctuation that is shown here. This is total heat release rate within the combustor, and m dot is this green line is the total evaporation rate, and this is the velocity. So this is actually the cross-sectional average velocity at the dump plane, which is also fluctuating. So you can see there is a phase difference of pi/2 between the pressure oscillations and the velocity oscillations, which is typical of air column vibration. And you can see the heat release rate is almost in phase with the pressure fluctuations. So we see that a combustion instability has occurred. So we can also take this pressure signal, apply a Fourier transform, and look at the frequency of the combustion oscillation, and that's shown here. So next, I'll talk about the cases where the VMFR model is applied. So here, you can see from case NA2 to NA5, we start applying this phase shift between the fuel flow rate fluctuations, which is shown by the black line, and the pressure oscillation. So when the phase shift is 0, so it's as we expect. So when the pressure is low, below, so the pressure above the fuel injector is low, you get some fuel injection. So this is the fuel injection period, and as soon as the pressure becomes high in the combustor, ideally it should be 0, but we are giving a small flow rate to keep that equivalence ratio at 1. And then as we increase the phase shift, you can see it starts showing up in these curves. The phase shifts match the applied values. So 90, 180, and 270. So here, another important observation is that for case NA2, you see the pressure oscillation amplitude is not so strong. It's a weak combustion instability. But as we start increasing this phase shift, you can see the amplitude starts increasing. And so I'll show you the animation for this case NA4 so that you can have an idea of how the fuel injection is varying. So you can see, of course, there's a strong recirculation happening here, and the fuel the injection period starts, and then it cuts off. Again, it starts and cuts off. And this is based on the injection period and the injection rate is based on this model that we are applying and the phase shift that we are applying between the flow rate and the fuel flow rate and the pressure oscillations. So then we also look at how the other quantities are oscillating, like the heat release rate and evaporation rate and velocity. And again, like there is, in all cases, the velocity and pressure have a phase difference of pi/2, is consistent. But as we increase the phase shift, you can see the other quantities such as the evaporation rate and the heat release rate. Well, heat release rate is almost in phase with pressure, but the evaporation rate starts to show some different phase relation as the phase shift starts increasing. And another important point here that I want to say right now is, if you see the velocity fluctuations for especially these cases where the phase shift is large, so when the velocity is very low, your fuel injection rates are quite high, and this will have impact on the combustion instability characteristics, which I will explain briefly, shortly, I mean. And then, so this is all the animations for the cases from NA2 to NA5. So you are applying the variable mass flow rate model and with different phase shifts. And these videos are shown for 6 cycles of pressure oscillation, which is shown by this schematic. And you can see there is this red line that is traversing along the time axis. So that red line indicates the time indicated by this red line corresponds roughly with the time in these movies. So you can see case NA2, not such a strong combustion instability, but as you start increasing this phase shift, there's like more violent, there's sudden heat release occurring, like the temperature suddenly rises. And you can see that when the fuel injection starts, you can see these droplets have a certain amount of residence time. And this is because, as I pointed earlier, when the fuel injection starts, the velocity, incoming air velocity is small. So because of that, when the droplets injection starts, you can see the droplets are still residing in the vicinity of this backstep. And what that will do is it will give the droplets enough time to evaporate. And then there is a lot of pre-vaporization, and that evaporated gaseous fuel then flows into the combustor, and there's sudden heat release. And in case NA5, flashback also occurred. So if you watch closely, so when the animation begins here again, you can see the flame jumping upstream. There is like going now, and then like you will see now. Yeah, see, it started jumping upstream. So we couldn't run this simulation for so long because the flame eventually propagates into the inlet duct, and it just creates issues, numerical issues. Well, I don't think it created numerical issues, but it's just the combustion instability. After a while, it just started growing and growing. So next, So next I'll show you some of the characteristics of the combustion instability happening. So first here we have the case NA1 where there is no model is applied. The model is not applied, and you have a certain RMS value, the pressure oscillation RMS value shown here for the different cases. So as expected, when you apply that model with zero phase shift, you can see a drop in the pressure oscillation intensity, which is expected. We saw very weak oscillation. And then as we start increasing the phase shift, the pressure oscillation intensity starts rising. And then we can look at why this is happening in terms of the Rayleigh index. So you plot so these are the span-wise average local Rayleigh index distribution shown for all the cases. So you can see case A has, there are regions of positive Rayleigh index, which shows strong correlation between heat release rate and pressure. But for case NA2, not so much. And then as we start increasing the phase shift, you can see this positive region becoming more and more predominant, indicating stronger, the coupling between heat release and pressure perturbations is getting stronger. So yeah, and another important thing is this positive region is also moving upstream as we increase the phase shift. It's going closer to the dump plane, and we want to. So this is also one of the peculiar features that we found. So we want to know why this positive regions of positive Rayleigh index regions move upstream. So for that we looked at the So to look at it more quantitatively, what you can do is you can plot the streamwise distributions of cross-sectional average local Rayleigh index, so which is plotted here for all the 4 cases with where the model is applied. And you can see, like, from case NA2 to case NA4 and 5, like 5 we couldn't run it, so I think we don't have sufficient statistics because we couldn't run it for a long time. But then you can see this positive peak of Rayleigh index is moving upstream. So 0 is the dump plane. So 0 is where the backstep is situated. So you can see it's moving upstream. And the reason for this is, like, when we look at the streamwise distributions of the phase and cross-sectional average local heat release rate. So this is the phase-logged heat release rate distribution for the phase of, so here the phase 90 means when the pressure is peak at the max pressure. So you can see the heat release rate distributions also show a similar tendency where the peaks are moving upstream. So mind you, this range is not the same. So, but it is like the peak is moving a bit upstream as we increase the phase shifts between pressure, the fuel flow rate fluctuations and the pressure oscillation. And the reason why the heat release is moving upstream will depend on the spatial distribution of the heat release rate. Depend on the spatial distribution of the mass of the gaseous fuel at a phase or a time instance immediately beforehand. So that's why we look at the streamwise distributions of the phase averaged local fuel mass. So this is the evaporated fuel that is available, and you can see again it shows the same tendency, like the evaporated fuel, as the phase shift increases, the peak value of the evaporated fuel is also moving upstream. And this is shown for a phase of the time instance or phase of phi equal to 0, which means this is coming before this phase. So at this instance, the pressure, if you see the pressure oscillation, it is P is equal to that atmospheric pressure. And then if we look at the reason for why this tendency in the local, the local fuel mass, we have this kind of tendency, we look at the evaporation rate, because the amount of fuel available will depend upon how much fuel, how much evaporation rate, or the evaporation rate at the phase before this phase. So we can see the similar tendencies happening there. So this, as I said before, you can see as we increase the phase shift, there is in case Na4 especially, there is a localized peak in the evaporation rate. And this is precisely the reason that I cited before, because when the fuel injection period occurs, the velocity, inflow air velocity is very low, and that gives you enough residence time for these droplets to pre-vaporize, and that's why near the dump plane you see a lot of a very high evaporation rate, and then that then the evaporated fuel in the next phase is like shown here. So that's the reason. So that's the chain of events that leads to that strong Rayleigh index, positive Rayleigh index that we saw earlier. So yeah, I mean, this is again explaining the reason why you can see when the fuel injection is starting, the velocity of the incoming air is decreasing. So it increases that residence time. So to conclude, we applied this, we used LES and to study the turbulent spray combustion field in a backstep flow combustor, and we investigated the effect of temporal fluctuations in the fuel flow rate on spray combustion instability. And so for that we proposed this simple VMFR model, and we found that the temporal fluctuations of the flow rate of liquid fuel, these create strong influence on the combustion instability intensity, and as we increase that phase shift between the flow rate and the pressure oscillation, the combustion instability became stronger. And also, as we increased the phase shift, we saw that the heat release rate near the dump plane also increased because as a consequence of the increased fuel droplet residence time and the subsequent localized increase in the fuel droplet evaporation rate. So this strengthened the correlation between heat release rate fluctuations and the pressure oscillations. So how much time do I have? Couple of minutes. So I wanted to actually talk about the combustion noise, but since I am running out of time, so I have only 2 minutes, is it? Okay, so I think I'll conclude, but just a moment. Maybe I can just show you yeah, so we are also So we are also doing studies on combustion noise. So what we do is we apply these hybrid CFD-CA coupling approach, where you solve the reactive flow field of the flame using a CFD, like either DNS or LES. So I performed the DNS, and then from the DNS solution you can get some source terms, acoustic sources, which can be then used. They are then transported from the DNS mesh, interpolated from the DNS mesh to the CA mesh, and then in the CA solver you can solve, you can use different strategies. I use the acoustic perturbation equations to solve the propagation of noise, and that is shown here. So you have the acoustic sources, which is the orange contours, and then you have these grayscale is showing you the pressure perturbations. So this is something that I'm also engaged in, and if you are interested, you can, people who want to look at my study in detail, you can refer to this paper, or you can send me an email, I'll send you this paper. So that concludes my talk. So thank you very much for your attention. Thank you very much.
The paper is now open for comments or questions. And please identify yourself.
Hello, Dr. Shayok Banerjee from IIT Hyderabad. Have you tested the impact on choosing different chemical kinetics for on your instability simulations? So have you tested different kerosene kinetics?
For this case?
Yes, this case.
Not at the moment, but if you see, this simulation is performed using like almost 21 million grid points.
Yeah.
So it's, I mean, for an LES, this is still huge.
Yes.
And each case takes about like 1.5 to 2 months, depending on
Okay.
which machine we run it on.
Okay.
So, but we do want to investigate this issue, as you pointed out. So that's why, as a next step, we want to apply the flamelet approach. So we found that when we looked at the Rayleigh index of all these cases, we found that the combustion is mostly premix. So we can like try to incorporate some kind of FGM and then see whether the results change or not. So we are in the process.
Effects on the emissions due to instabilities, is there any future work you are planning to do on that?
Well, at the moment, we have no such plan for the emissions, but if there is something, we can, you know,
okay,
talk
good.
about.
Thank you.
My name is Gunbir. I'm from Mechanical Engineering Department. So I wanted to ask that what is the role of choosing a non-equilibrium evaporation model as compared to an equilibrium evaporation model? And does it have any link to the heat release rate fluctuations which you are observing?
Yeah, so the reason is because the droplets that you see, if you see the droplet size distribution, yeah. So here, if you see, most of the droplets are less than 50 microns. So at a small size of the droplets, this non-equilibrium effect becomes important. So what I mean by non-equilibrium is like the way it is modeled. Maybe I have a slide here. So, okay, I'll show you the governing equations later. So what it means is, depending on the amount of vaporized fuel on the droplet surface, its evaporation rate changes, and this is taken into account using that Langmuir-Knudsen model. So if the droplet was big enough, maybe you can do well with your equilibrium assumption. But at small scales, previous research has shown that the equilibrium model doesn't work well. So of course, this will impact finally your heat release rate, because the evaporation rate decides how much fuel is converted into gas phase, and that will decide the local equivalence ratio and the heat release rate. So we can discuss later. I can tell you more about the model. I can't find the slide here. So yeah, thank you very much for the question.
Hi Professor, this is Vignesh. I'm MTech student here, Aerospace Department. So can you please go to the slide where you show FFT case for case NA1?
No.
So, my question is more of a doubt that at which point you measure the time series?
Sorry, I didn't mention. So this pressure, the pressure shown in all these graphs is measured at the dump plane. So dump plane means this location, the step location. So you have the inlet duct and this is the combustor, right? So this is the dump plane, this cross section. So we measure the pressure at a point just above this surface at the dump plane, so somewhere around here.
Okay, and what was the vortex shedding frequency for this case?
So it should be the same as this, right? Vortex, because if you see the velocity fluctuation, the frequency of the velocity fluctuations is almost same as the pressure fluctuations. So it's the same. It's the same periodicity.
So you are saying it is around 600 hertz?
Yeah, because these the time scales in these simulations are very small.
Okay.
They're like of the order of 10 to the power minus 7 seconds.
Okay.
So that's why it's an expensive simulation.
Okay. Thank you.
Thank you very much.